that's all for our criteria. The next topic that I'm going to do, and this topic is, it's not difficult, but it combines whatever we have learned from week 4 to today. Okay, so wait. So this structure that we're going to do, the only thing that we don't perform is buckling. I repeat again, the only thing that we don't do is buckling. So we're going to apply whatever we've learned after buckling to today's lecture. Okay, so let's do it. Okay. Okay, so we're going to look at this structure over here. Okay, so this is our example number 2, or not example number 2. We are going into design and analysis of beams with 3D mold circle. Okay, so let's look at example over here. As I said, we are going to apply whatever we have learned. Okay, let's look at example. Okay, we have a steel that is rolled and given the support loading. Okay, so we have to satisfy the requirement that the average stress is less than, or the maximum stress is less than the allowable. So the structure that's selected is W250 28.4. We are going to determine the maximum stress in the beam, the maximum value of the principal stresses at the junction of the web and flange. Now, this is a very interesting problem. Okay, so this structure over here is what we call a overhanging beam. Okay, it's what we call a overhanging beam, and it mentioned to find the junction. So if we were to look at this I-beam that's been used, the failure region is here. Okay, so these are our failure region. Why there's a failure region? Because you have a what? You have a fillet radius. I will not teach in this course, okay? Those of you who are in mechanical engineering, you will learn this in 3E03, which is the next course that you're going to do. Okay, so the fillet radius is a stress concentration. Okay. So at the fillet radius, you're going to have very high stresses, and the failure will occur in the junction of the what? Of the flange and the junction of the web. Okay, so this is well known. If failure is going to occur, it will not occur on the this furthest distance away from the centroid, or it will not fail at the centroid. It will fail at the junction of the of the flange and the web because of the fillet radius, and the fillet radius is a stress concentration. Okay, so two formulas we're going to apply. Okay, as you can see down here, if we were to put in our transformation, we call this our x, y, This is our rotation in our Z, and in our view over here, this is our Y, and this is our Z. This is our rotation in the X. So we know that the structure is under bending moment, okay? And we know that the bending moment is only in the Z direction. So one formula we're going to apply is we know that the normal stress in X is equal to mz over izz multiplied by y. Okay. Then you guys will ask me, Eugene, how about the shear? So we know that this is a thin wall. Right? All the flange is thin wall analysis. So if we were to, I'm going to copy this. So if we're going to sketch the shear flow, right? We're going to sketch the shear flow. So we know that we have what? We have a loading applying from the top, right? So this is Vy, and we know that this is flowing this way. And this thing is going down, and then it's flowing this way. And we want to look at the junction over here, right? So if we were to draw transformation, so transformation, this is our Y, this is our Z, this is rotation in our X. So the formula that we're going to do, so we know that the shear, right? The intersected, so this plane, that's kind of the intersecting plane in the X, and the shear is in the Y. This is equal to shear YX, and this is equal to Vy over IZZ, because I call this Z axis, okay? Vy over IZZ, right? So I call that ZZ. Vy over IZZ QZ divided by T. Okay. So from here, we if we were to place our element at the junction, okay, if we were to place an element at the junction, right? So if this is our element now, maybe that is not a very good position of our junction. Sorry. So now if I'm going to put our element, okay. So I don't know exactly which position to calculate yet. So I'm just going to put my element down here. Okay. So if that is our element, right? So this is our X, Y, and then we're Z, right? So we know that we are going to have a what? Normal stress X, right? Because we have to calculate. And then we have our shear. So this is shear XY is equal to shear YX. And it's equal to Vy over IZZ multiplied by QZ over T. Okay. So that's how you have to view a problem. Okay, that's how you do it. So the thing now is we have, so stress X. So let me highlight what is the issue over here. Okay, we need to locate, okay, position where mz is what? Maximum. Okay, right? We also have to locate position where Vy is what? Maximum. Why is that case? Because Y and IZZ, QZ, T, and IZZ are all constant. The only thing that's changing is MZ and Vy along this beam. Okay, at different position along this beam, right? We are going to have maximum bending moment or we are going to have maximum what? Maximum shearing stress or maximum shear force. So to solve this problem, you have to first locate positions, okay, where MZ is maximum, or sorry, all this can be a single position, or locate positions where MZ and Vy are not equal to 0. Okay, why that's the case? Usually, when MZ is at its maximum, okay, there's a possibility that Vy is equal to 0. Okay, there is a possibility. Okay, so that is what we call that's what we call the relationship between shear force and bending moment diagram. Okay, so before or not before. Okay, so now what I want to do now is again a very interesting feature when we look at these two formula. Okay, when we look at these two formula over here. Okay, when you look at these two formula, there's a very interesting feature that comes in. We know where failure will occur. Okay, we know where failure will occur, but I want to highlight this to you. If you were to look at two formulas, right? I want you all to look at two formulas, right? So I want you, first of all, if we were to focus where stress Y or stress X is equal to My over Izz Qz divided by T, right? So if we were to now sketch, if we were to now sketch the distribution, so this is our normal stress in the X action. This is our Y. Okay, so I'm going to have a assumption that this is the top is in compression, the bottom is in shear. We realize that we get this trend. Okay, so the point of interest for us is along this line. Okay, the junction, right? This is our point of interest. Right? We want to know what is this value over here. Okay. Now this is the normal stress distribution, right? If we were to look at the shear stress distribution, it gets even more interesting or exciting. That's why I every year I teach this course twice in a year, because this you have to have the passion to transfer the information to students. Then you realize how critical this course is. Okay, so now if we were to look at the shear, right? So you have the shear xy, right? And then you have your y value. And then we have our shear xy is equal to Vy over Izz Qz divided by T. Why I put Qz over T is My multiplied by, sorry, too excited again. My over Izz multiplied by the distance y. Okay, so multiplied by y. Now, if you look at over here, Qz, how our distribution look like? So our distribution will look like this. Right, just to help you quickly recall. We start from 0. We come to, it's a curve. Come on. We start from 0. We come to here. Because of the change in thickness, we have a step function. And then it does this. and then it comes here, and then it comes to 0. Okay, so this is the point we would like to determine. What is this shear XY value over here? We don't determine the shear max because the normal stress is equal to what? Is equal to 0, right? Okay, so this is the cross-sectional aspect, right, that you can see. That's why we are asked to determine what are the stresses here and here. And then we have to locate the position along this axis, okay, along the x-axis, where our mz is, where is the maximum Vy, or position of we have relatively high mx and Vy values. Okay, so now you know the procedure of solving this problem and the complexity. Okay, I mean it's complex because we combine different topics, not necessarily complex as in mathematically impossible. Then after this we have to apply what? 3D mold circle. Okay, so from here, after that, we construct our element, then we do our 3D mold circle. Okay, I'm going to stop here. Tomorrow, I'm going to post another homework, and I also post the answer at the same time, so that you can study for your finals, which will be held on August the 8th, and it's a good number. Okay, August the 8th is a good number. Okay, I'll see you guys next week then. Bye. No, Thursday. Bye.